This is an IDE that I created for the popular Lua game framework LÖVE. It's called LÖVE Studio. When you first open up LÖVE Studio, you'll see something that looks like this. First thing that you're going to need to do is click on Project and then New Project. And you'll see something that looks like this. Create a new folder. Type in the name of your new project, and then click Save. And now your project has been created, and it's ready for you to start coding. Now that we have our project open, we can press Ctrl-O, and we see a list of all the modules that are in our project. So there's a template that LÖVE Studio has, and whenever a new project is created, all of the files in the template are copied into the new project. The template is in your app data directory. You don't need to know where this is, but it's in a directory called LÖVE Studio /template under your app data directory, and it contains a bunch of Lua files, and they just get copied into your project directory whenever a new project is created. Basically, I've included a few of the most basic files that tend to be included in LÖVE projects. Main, for example, is necessary for any LÖVE game. The file that I included contains just some basic callbacks for loading, drawing, and updating. It also requires the globals module at the top of the file, and this means that globals will be required as soon as the game starts up. So here's this template globals file that I have, and the globals module actually has a special status among all the modules in a project, and that's because it's the only file which permits the programmer to define globals. If you try to define globals anywhere else, main for example, you'll get an error. Variable not in context. Okay, moving on. I've also included a conf file. It's just a standard file in a LÖVE project that defines all of the configuration settings for a game. And then I've also included this file, which is basic class system .class, and it's a Lua class system that I wrote, and I also wrote a static type checking plugin for LÖVE Studio so that classes which are defined in basic class system can be type checked statically. And if you try to modify basic class system .class, the type checking plugin for basic class system will cancel out your modifications. So if I try to save this, it just gets automatically removed. And then there's one more file. This is just a sample of a class implemented using basic class system. It's a 2D vector, so it's a pretty standard, useful class to have. And that pretty much that's what I've included in the template that comes with LÖVE Studio. Alright, so most Lua IDEs keep track of some basic API type data, like you'll be able to index into the LÖVE table and get a list of all of the modules that LÖVE defines, and for each module you'll get a list of all the functions that it defines, and you'll probably even get some typing information or a description of the types that are expected for that function. But that's pretty much the extent of the IntelliSense capabilities that Lua editors and IDEs tend to have. But LÖVE Studio goes a lot further than that. So for example, you could declare a variable called canvas, and then on the next line you could index into it and get a list of all the methods that it has. And the reason this is possible is because LÖVE Studio actually keeps track of the types of terms in your program. So on this line, for example, it evaluates the right-hand side, and it knows that new canvas returns an object of type canvas. So then the variable canvas gets bound to the canvas type. So from then on, whenever we try to index into the canvas variable, we get a list of all of the methods that the canvas type has. And this includes methods that were kind of inherited from supertypes, like type and type of, which are methods of LÖVE's object type. But a common programming pattern is to have a variable that starts out nil, and then later in the program it gets assigned to an actual value, a non-nil value. So here, for example, the canvas variable starts out nil, and then we try to assign it to a new canvas, except an error has been generated. It says that right-hand type canvas is not a subtype of left-hand type nil. So what happened was, in this case, the canvas variable got bound to the nil type, and the nil type is not very useful because the only value that it can refer to is nil, and it can't refer to canvases. So to work around this, we have to use a type ascription. And type ascriptions are just comments which are right above variable definitions, and they're formatted like this. It's the @ and then var, and then in parentheses a type name. And canvas is just a built-in type in the LÖVE API, but when you prefix a type with question mark, that makes it a nillable type. Nillable types can refer to nil, but they can also refer to values of the underlying type. So in this case, adding this ascription fixed our error, because canvas in this case is getting bound to nillable canvas. So we can assign it to both nil and actual canvases. I think that nil values getting passed around cause a lot of errors in programs. So making variables have nillable types by default, I think, would have been a mistake. Most of the time when you have a variable, you're assuming that it's not nil, and I felt that it would be a good idea to have the type system kind of reflect this by making nillable types a special case that have to be handled explicitly. One more thing about this type ascription syntax. After the ascription, you can add a comment. I don't think I would ever actually write a comment this lame. Got a dry throat. But So this comment, anywhere in the program you can hover over the canvas variable and then the comment pops up, and also it shows you the type of the canvas variable, and this shows us that our description worked. So yeah, that's how nillable types work. In addition to ascribing variables, you can also ascribe constants. Instead of typing var, just type const. And if someone tries to reassign the name that gets bound on the next line, they will get an error that says cannot assign constants. Annotations can also be used to supply functions with typing information. So for example, we define a function called myFunction with 2 parameters, and then we try to call it. Forgot to type the function. And then we try to call it. We do get some IntelliSense data. It knows that there are 2 arguments, but it doesn't know what their types are, so we can pass anything in for these arguments. But if we pass in the wrong number of arguments, it will generate an error. So we can supply the arguments with types by using param annotations. You type param, and then in parentheses you type the name of the parameter, colon, the type of the parameter. So now when we try to call it, we have the types of the 2 parameters given to us. So the first one is supposed to be a canvas, so we pass a canvas in for that. And the second one is a nillable number. Nillable types can be used to designate a certain parameter as optional. And whenever you have an optional parameter, it's probably good to include like a default value for that parameter in a comment. So since it's optional, we should be able to leave it out without getting an error. And we can. Or we can actually supply the argument, and that won't give us an error either. But if we try to pass in something of the wrong type, we should get an error, and we do. So in addition to annotating parameters, we can also annotate return types. You just use @ret, and then in parentheses you type a return type. We don't give names to the return values. We just specify their types. But the order in which the return annotations are given does matter. It's used in order to specify which return values are ascribed which types. So now if we call myFunction and we get the values that it returns, x should be given type number and y should be given type string. So if we index into y, for example, we get all of strings methods. Or if we try to concatenate something onto x, we get an error because X is a number, and concatenations for strings. Number does not define a dot dot operator. Okay, so that pretty much wraps up function annotations. I'm going to talk about how LÖVE Studio handles object-oriented programming. Instead of offering programmers a complete solution for object-oriented programming, for example, a class system, Lua provides programmers with tools that can be used in order to make their own object-oriented programming solutions, or making their own class systems, for example. So in order to accommodate this, LÖVE Studio has a plugin interface which allows programmers to write type checking plugins for specific class systems. As I've already mentioned, LÖVE Studio comes with a class system called Basic Class System, and I've written a plugin which performs type checking on classes which are written using Basic Class System. And in addition to type checking plugins, there's also an interface for plugins which can handle mundane details for defining classes. For example, if you want to define a new class in LÖVE Studio, you can press Control-N and it will bring up this Create Module dialog. And in this drop-down box is a list of every class system plugin that LÖVE Studio has registered. So for different class systems, there may be different interfaces for how one would define a class. So I have this plugin for classic style Lua modules, and since they don't have any inheritance or any notion of inheritance, I don't have a parent class field like I do for Basic Class System. So I'm going to define a new class using Basic Class System as an example. And I guess I'll call it elf. I don't know. Okay. So there is this template in the Basic Class System plugin that will be used to start class definitions with some bare bones boilerplate code. So in Basic Class System, first of all, constructors are defined by adding an init method to the class being defined. And inside the constructor, you can assign values to fields of self in order to define new data members. So if we want to give this elf a position, for example, we can give it X and Y fields. And these are actually treated as data members. So if we define methods of elf, like for example, we can define a get position method. Inside this method, all of the data members of elf will be accessible. So if we type self and then period, we will get a list of all of elf's data members. X and Y are the ones that we defined. Delegates and events get automatically added to each class, and I'm going to talk about those later. But for now, X and Y, not only does it know that they're data members, but it also knows what their types are. They're both numbers, because we both assign them to numbers, specifically 0. So we can assign these data members to other number values, but we can't assign them to values of different types. For example, we're not allowed to assign them to strings. If we do, we get an error message. Defining a variable which takes on values of different types throughout a program will most likely lead to errors. So I've decided to detect these situations and generate errors whenever they occur. So if we try to access a field that wasn't declared in the constructor, we'll also get an error. In this situation, it'll say this class does not have a field called Z, or whatever your variable name is that you tried to access but doesn't exist. It's generally a good idea to have a definition of all of the components of a class in one place. You don't want objects of a class to kind of change shape during the execution of a program, and specifically you don't want to be adding new data members to them after they've already been constructed. So generating errors in these types of cases, I believe, is also a pretty good idea. Alright, let's see. LÖVE Studio differentiates between data members and methods. So if we type self and then period, we'll get a list of all of the class's data members. If we type self colon, we'll get a list of all the class's methods. The type system does not allow you to access methods using a period to index. So you can't do something like local a equals self dot get position. An error will be generated in this case. I don't want programmers to be able to get access to a method or a pre-method that does not have a self argument applied to it, because then they could pass in other objects for self, and that would not be good. So I limit method access to the colon operator. This way, whenever a method is accessed, self is automatically applied to it, and it must be called right there. To instantiate our class, we first need to require the module that our class was defined in. To do that, just press Ctrl R, start typing in the name of the module, and then when it becomes selected, press Enter. It'll insert a line like this near the top of the file. It creates a new variable named after the module, which is assigned to the result of requiring the module. So this variable now refers to a constructor for our new elf class, and if we call it, it will return a new elf. So new elf now refers to an elf instance. So if we index into it, we get a list of all of elf's methods. And for reference, I'm going to open up the elf module. As we can see, it only defines one method, get position. If we index into it using a period, we expect to get, we might expect to get X and Y listed, except in basic class system, all data members are protected, so they're not accessible externally. In basic class system, all data members are protected and all methods are public. But there are two fields that we get when we index into new elf or an elf instance externally. We get events and delegates. Delegates is just a table which contains a element for each method. and each of these elements are equivalent to the corresponding method with a self argument applied. So for example, in this case, getPosition is going to be the getPosition method with newElf partially applied to the self argument. So like if we did something like this, x and y are going to both be 0 after executing this line. Alright, so that's delegates. Now events. An event is kind of like a method. You define them inside of a class like this. Class events some event. You assign them to an empty table constructor, and you can also give them param annotations. So now, when we look into the events table, we'll get a list of all the events that have been defined for that class. And in this case, we just have one, some event. So each event is going to have two methods that you can call externally. One allows some external source to subscribe to the event, and the other one allows an external source to unsubscribe to the event. So if we call subscribe, we can see that it expects a function which takes two numbers and doesn't return anything, and that matches the annotation that we provided. So basically what this does is every function that subscribes to some event will get called whenever the some event occurs, and that happens whenever we trigger some event from within our elf class, and we do that by calling some event as if it were a regular method. And the arguments that we pass into some event will get passed to each subscriber when it gets called. Let's see. Unsubscribe is a very similar function. It just removes a subscriber from a list, from the existing list of subscribers. It takes a function with the same signature, obviously. Alright, so that's pretty much everything about events. Basic class system also supports single inheritance. To inherit from a class, you just press Control-N and then make sure the basic class system plugin is selected, and type the name of your new class into the class path. And then in the parent path, type the name of the class that you want to inherit from. So when you start typing, it'll autocomplete for you. But if you type in the name of a module which wasn't defined using basic class system, it won't autocomplete. And if you try to use the name of a module that wasn't defined in basic class system as a parent class, it will generate an error message. And make sure that you can only inherit from basic class system classes. So once you've chosen a parent class, click OK, and it will create this new Magic Elf class for us. Alright, so since data members are protected, we have access to all of the protected data members within the methods of the Magic Elf class and within the constructor as well. This line right here was inserted for us. It's a call to Elf's constructor, and that has to go at the top of the the magic elf constructor, so that all of elf's data members have already been assigned once we get into the magic elf constructor and start using them. So when you inherit you automatically get all of the methods and data members of the class that you inherit from, and you also get, as I said, you get its methods, and you also get its events. If you try to, LÖVE Studio will ensure that the derived class defines a type which is a subtype of the class of the base class that you're inheriting from. So if you try to do something that is inconsistent with this subtyping relation, an error will get generated. So, like if I try to redefine some event, this, what's this? Oh, it should be magic elf. So if I try to redefine an event, that's okay because the type of some event matches the base class. But if I were to change one of the parameter types to string, for example, an error would get generated, and sometimes these subtyping errors can be pretty cryptic, but it shouldn't be. From reading this, you should be able to figure out what went wrong. So now that we have this subtyping relation, we can use magic elves in any context where elves are expected. So like, one thing that I haven't mentioned is that when you define a new class, you can now mention that class's type in type annotations, and a class's type is just the name of the module that it was defined in. So instead of having our second argument of my function be a knowable number, we can make it an elf. So now when we call my function, let's see. We have to pass an elf in as the second argument. We can no longer pass in a number. We'll generate an error. But we can also pass variables that have types which are subtype of elf. So, like a magic elf, for example, you would be able to pass in. So if I require magic elf, this should work. I don't get any errors. That's because magic elf is a subtype of elf. However, if I were to change the argument type to magic elf, and then pass in an elf right here, that would not work, because even though magic elf is a subtype of elf, elf is not a subtype of magic elf, because you can't use an arbitrary elf in situations where magic elves are expected. Because, for example, if you tried to call the cast spell method, which magic elf has but elf doesn't, on just an elf, that wouldn't work. That would cause an error. So we don't let you pass in elves or magic elves are expected. Let's see. As I've mentioned, I think that nil values getting passed around lead to a lot of errors in programs. Whenever a programmer declares a new variable, I think they should try to figure out a way to give it a non-nil type, because variables with non-nil types are just much easier to work with. You don't have to worry about these variables being nil at certain points in the program, so you don't have to use if statements to check whether or not they're nil. That kind of a thing can easily increase the complexity of your code, and oftentimes it's not really necessary. But sometimes for quick and dirty programming, you do need nillable types. So this leads to a dilemma, though, because if you have a variable which is bound to a nillable type, like let's make a variable called z, or yeah, let's just call it z, and let's give it a nillable number type. What happens when you need to pass this variable into functions which expect non-nil numbers? What happens is you'll get an error, and this is good because why would you give a parameter a non-nil type if you could just pass nil in for it? So this is good that we're generating an error here. But what happens if, for example, we have an if statement checking whether or not z is equal to nil? And what if we want to pass z into cast spell right here? Well, because we have this condition which checks that z is not nil, we should be able to promote z to a non-nil type inside this the body of this if statement. And that's exactly what happens in LÖVE Studio. And this allows you to interface between code which uses non-nil types and code which uses nillable types. So if I were to move cast spell into this if statement, no error occurs. So if we hover over the z variable, it'll show us the type of z, and it says, first it has question mark number. Okay, that's nillable number. That's the type that the z variable was initially bound to. But then in parentheses, it just has number, so it has non-nil number in parentheses. And that type in parentheses I call an accumulated type. And that's basically a type that we have determined the variable to have based on the surrounding code. So in this instance, it would be the condition of the if statement. Basically, I tried to implement this so that the type checker is pretty smart about when it can and cannot make type accumulations. So, I mean, obviously, outside the if statement, the accumulation goes away because you don't know whether or not that if statement is actually going to get taken. Let's see. And if I were to do something like this, okay, this is obviously not going to work because z has accumulated type nil here. But if we were to use an else inside this block, we know that the condition for the first block is not true. So that tells us that self.z is non-nil in the second block. So we should be able to call cast spell here using z as an argument. And as we can see, non-nil number has been accumulated there. Okay, so in addition to using the conditions of if statements to generate type accumulations, we can also use assignments. So for example, if we assign z to 3 right here, we would accumulate a non-nil number onto z. And of course the rule is, we can only accumulate types which are subtypes of the type that was initially bound to the variable. So string, for example, would not work. Of course, we would get a type error if we tried to do that. I think that's basically all you need to know about type accumulations. Okay, so now I'm going to talk about function type annotations. Since Lua has support for higher order functions, functions often get used as arguments to other functions, and we can annotate function arguments to specify that the expected type for that argument is a function. In order to write a function type, you just use square brackets and then a list of all of the parameters for that function, and a list of all of the parameter types. So let's say a function that takes 2 numbers and returns a string. So you separate the parameter types by commas, and then arrow, and then a list of all of the return types for that function. So it was just going to be string. And of course the list could be empty. If there are no return types, you just use open square bracket, close square bracket. So now if we call x inside this function, we should get an appropriate call tip. It tells us that x takes 2 numbers and returns a string. So that's good. There's also a different family of function types called latent functions. A latent function is a function which can call other latent functions, one of which is coroutine yield. So a latent function can call functions which may not immediately return a result. They may yield and not return a result until several other resumes later if we're in a coroutine. So basically, like if I, in order to annotate a latent type, you just place an L between the dash and the angle bracket of the arrow. So if we were to try to call x inside cast spell, we would get an error because cast spell is not latent. If we want to make it latent, we just need to add a latent annotation to it. Calling functions and not knowing when they're going to be returning can be kind of confusing, and that's why I added latent functions into this type checker to try to help people identify which functions might yield and which ones won't. So because latent functions can only call other latent functions, and because the base love callbacks are non-latent, you might be wondering how a latent function ever gets called in the first place. And coroutine create takes a latent function to spawn a coroutine with. So that's basically the source of a latent function call. And then of course coroutine yield is itself a latent function. So if you try to call it from a non-latent function, you'll get an error. Now I'll talk about records. If you assign a variable to an empty table constructor, it will be bound to type unknown. And a variable of type unknown is just a variable that the type checker does not know the type of and doesn't keep track of. So it'll allow variables of type unknown to appear in any context. You can add fields to variables of type unknown. You can call methods on them. You can add them to things. You can do anything with variables of type unknown. And as a side note, if the type system is ever restricting you, you can cast anything to type unknown. So, you can do this. Without getting any type errors. So that's a nice way of bypassing the type system. But unfortunately it's very unsound, and furthermore you don't get auto-completion for variables of type unknown. So if you do want a table and you want to have auto-completion for its fields, what you can do is declare the fields inside the table constructor. So now we do get auto-completion. And now Z has type record, or it has a specific record type. Let's see. And it knows the type of the fields of the record. So if we try to assign one of its fields to some other type, like a number for example, we would get an error. Another interesting thing is that you can define, or you can add var and const annotations to fields of a record. So do something like this, and this would prevent us from reassigning A to some other string. It should say it cannot assign constants. Okay. But I mean, we can still treat A as a string. We can access any of its methods. So that's useful. Another thing that you can do is use the sequence form of a table constructor. Just a bunch of expressions separated by commas. Now we can iterate through the sequence in a type-safe way. So that's pretty cool. And if we try to, index it with a string, we should get an error. Alright, so the value type of a sequence table is taken from the first element of the table. If some other element has a different type, an error gets generated. Alright, so that's how you use tables in LÖVE Studio.